So, can you see my screen?
Yes, sir.
Yeah. So let us wait for 2 3 minutes. Okay, so I think we can start now. It's around 6:05. So let me project my screen. So is this visible to all?
Yes, sir.
Yeah. Okay, so hello everyone. So this is the first live session of the course Physics through Computational Thinking, and the course ID is this NOC23PH02, and the instructor is Professor Aditya Sharma from Aizer Bhopal. So I am Javed Akhtar Mondol. So I am a PMRF scholar in the Department of Physics, IIT Kanpur. Uh, so I work under Professor Shoykot Ghosh in the field of quantum optics. So you can check if you want in my website. So these are so since this is the first live session, so we will announce some general uh, thing. So first of all, the session will be on every Saturday from 6 to 8 p.m. and this is a 8-week course. So this is around of 2 hours, and since this is online session, so there may happen some technical issues and the meeting can get disconnected. So if that is the case, so I request you all to please join within few minutes with the same link that has been provided to you, and the session will be recorded and the video will be uploaded to the YouTube and the link will be shared with you. And so if there is any question, so since this is a live session, so this is interactive session, so if you have any kind of question, any kind of doubt, so you can you can interrupt me at any point of time, and if you want, you can write down your queries in the chat box also. So I will try to answer them. And this is the link of my website. So you all can call me Javed. So you don't need to call me sir. So this is kind of annoying. So just call me with my name. And so with this, so I think we should start. So so in this course, we will learn some basic mathematics, some basic computational with the software called Mathematica. So why we are using Mathematica? So there are other kinds of software also, like this MATLAB, and there are Python and C++, all this. So what is the advantage of Mathematica? So Mathematica is basically uh, will is a really useful tool to do symbolic calculation. So for example, suppose you have an equation of this kind. So 1 plus x to the power n. So let's suppose n can be 10 or something. So you want to find the coefficient of any power of x. Suppose you want to find the coefficient of x cube or x to the power 5 or this. So this can be easily done with the help of Mathematica. So Mathematica is really helpful and is really a powerful tool in dealing with this symbolic type of calculation. So, before proceeding, so do you have any kind of question regarding the session and all this YouTube video link and all that? Hello, hello, can you hear me?
Yes, sir.
Yeah. So, if there is no question, so we can proceed. So, do any one of you have any kind of doubt from the from this lecture of this week? Like, if any specific kind of queries? Okay. So, if no, that then we can proceed. So first of all, first we will learn to like with the help of Mathematica. So we will start from basic. Like from Mathematica we can calculate the like precision of any number. So suppose what is the importance of precision? So precision is really useful tool is really useful in this the research that are going on. So suppose in case of atomic physics and all that, the transition frequency, in that case the precision really matters. And if you want to find the we want to find the precision of our experimental finding with theoretical finding, then we want to compare the experimental result with theoretical result. So in that case, the precision of any number to a certain extent that really matters, and we can easily calculate the precision of any number with this help of Mathematica. So suppose we are given an constant. So suppose exponential. So we can someone wants to join. Yeah. So suppose we have our exponential and we want to calculate the precision of this exponential. So if we just type this, so we will get the value of this of our exponential function, and this is this 2.71828. Now if we want to increase the limit of our digits, suppose we want to calculate this up to digit 20. So if we type that, we will get this exponential value up to digit 20. So in that way we can get the up to what digit we want of any number. So suppose we have another function. So suppose we are given a function. So this is exponential of pi square by 4. So if we just calculate the value, so it will give us this value. And if we want to calculate precision up to, suppose up to 60 digit, so we can get precision up to 60 digit. And in that way, we can get also precision even up to in around infinity. So in that way, we can get the number up to any digit we want. So the so for the next tool that we use, so let us learn about this plot function. So what does this plot function do? So suppose we want to plot any so suppose we want to plot x, and what is the limit of this, so and let us take the limit from minus 10 to 10. So if we do this, so it will give us the plot of this function. So in that way we can plot any function that we want. So let us plot the sine function. So so this is the plot of the sine function, and so is my screen visible to all, like is the numbers and all this all can see?
Yes, sir.
Yeah. So so now suppose we want to see, like so suppose we have a sinusoidal function and we are modulating its amplitude with another sinusoidal function. So what will be what will be the effect of this amplitude modulation? So suppose that we want to see. So for that so that we can easily see through this plot function. So let us do that. So suppose we, and we have to specify the limit of this time. So the limit, let us suppose from 0 to 1, and if we plot that, so let us reduce the frequency. Yeah. So now we want to vary its amplitude. So let us so suppose this is for constant amplitude, we are getting this. Now if we modulate the amplitude with another sinusoidal function, then what we will get? So let us uh, vary its amplitude, so 2 pi. So if we modulate its amplitude, then we will get this. And so here we can from the command manipulate, we can manipulate this frequency also. So let us manipulate this frequency and let's see what happens to the signal. So so for that we have to write manipulate, and what we will manipulate, we will manipulate the plot. So plot, and we are plotting here this so suppose sinusoidal function to sine. So let us take a to be the manipulation factor, a into t, and we multiply this with our fixed signal. So sine 2 pi, and the limit of the time. So let us take to be from 0 to 1. And what we are manipulating? We are manipulating the constant a here. So let us we have to define the limit of a to which range we want to manipulate. So uh, define this from point 1 to 1. So point 1 to 2. So if we don't specify anything, then this manipulation factor a, it will default start from the value 1. So you can see that. So I think yeah. So this should be capital. Yeah. So we can increase the time. So if we don't specify anything, then our this a will take the initial value. But if we want our a to start from any different value, then we have to specify the value here. So suppose you want to start from 1, then a plot will look like this. So in that way, if you change a, you can see that the signal is changing. So in that way, you can get a visual feel or representation of how the amplitude is being modulated here, and what is the consequence of the frequency that with which we are modulating. So if we are what will happen to the signal if we increase or decrease the our modulation frequency. So, does anyone have any question? Okay, so I guess no. So we can proceed. So now since this plot function, it give us a visual representation of any kind of function. So we can check about specific properties of any function, like if it is continuous, or if it has some kind of asymptotes. So what are asymptotes? Like for, so suppose we have a function, and the function is dependent on a parameter. So f of x, it depends on x. So what will be the value of this function for large value of x? So it may happen that the function is converging to the x-axis, or the function is converging to the y-axis. So that is the asymptote. So we can check, and we can also plot two or three graphs together. Then we can compare what are their intersection point, and if they even intersect at all, and all this kind of thing. So let us take two or three function and let us plot them. So let us plot x to the power half. So we will take more than one function. So we have to, and let us take another function, logarithmic. So logarithmic of x, and we want to plot this with x. So we have to define the limit. So let us take x from 1 to 10. So now we don't know which graph correspond to which function. So for that we have to insert legend here. So for that we have to write the command plot legend, and in the plot legend, so we have to define arrow. So for arrow we will press the uh, uh, hyphen, and after that greater than symbol, and that will produce an arrow. And what will be the legend? So we can specify the legend here. So we can write expressions. Then let us see, and it will so if we write this, then the expressions that we are giving of the function, so they will show here. And so this graph corresponding, this blue one, this corresponds to this x to the power. So yeah, so this blue one, it corresponds to this root under x, and this orange one, okay, and this orange one, this corresponds to the logarithmic. So we can change the limit and see what are their behavior in for larger value of x. So let us take this from -10 to 10. So if we see here that these two graph, so they are never they are not intersecting. So you can increase the range of this plot to see if they are intersecting at all. So this blue one, this has higher curvature, and this orange one, it has lower curvature. So they will never intersect. So if we keep on increasing our limit, so they are never intersecting. So what does that mean? So if you write the equation, so if you write the equation x to the power half equal to log of x, so this equation, it doesn't have any solution. So because this x to the power half and logarithmic of x, they are not intersecting. So in this way, so if you have any kind of given equation, and if you are asked to solve that, if the equation does have any solution, that means if they ever intersect, so if, for that you will have to find the intersection point. The It means that if the given equation have any solution, then they have to intersect at some point. And that intersection point, that you can check by plotting in mathematics simply. So let us take another equation. So x to the power 1/4 equal to logarithm of x. So does this equation have any solution? So for that we have to check that if these two function, does they ever intersect or not. So let us do that. So for that we have to plot both the functions. So for the first function is x to the power 1 divided by 4, and the second function that we are given, that is log of x, and we have to specify the limit of x. So from 0 1 to, yeah, so these two equation, they intersect at around this point. So with this one intersection means they have at least one solution. Now let us check if they have another solution or not. So for we have to check this for higher values of x. So let us check, and for larger range we can check. So it looks like that the yellow curve, its curvature is decreasing, and the curvature of blue one is increasing. So there may be another intersection point, so we will increase the limit of. Before that, let us put the legends. Yeah, so let us increase the limit further. Yeah, so they have another intersection point. So yeah, so around this point, so they intersect, and so this equation, it has two solution because they intersect at two different point. And if we keep on increasing our limit, then we can see that this curvature, the curvature of this blue graph, it is increasing, and the curvature of this yellow graph, it has higher increase than this blue one. So they will never intersect again. So this equation has two intersection point. That means if we solve our given equation, this, so if we solve this equation, so we will get two roots of this equation. So in that way, if you are given any kind of equation, you can check, qualitatively check, like what can be the intersection point and all this. But if you want to find the precise uh, value of this x for which they are intersecting, so then you have to do some analytic calculation. So for analytic calculation, so what does this intersection means? So these two graphs, so we have x to the power 4 and logarithmic of x. So they are intersecting, means that, so suppose let us take the intersection point to be x0. So at x0, the value of x0 to the power 1 by 4 and logarithmic of x0, they will be same because they are intersecting at this point. And as they are intersecting, so their derivative, or their rate of the rate of change of their value, that must be also same. So this derivative of this x to the power 1 by 4 at point x equal to x0, and derivative of this logarithmic function at point x equal to x0, so they must be same. So if we solve these two equation, we will get our value of this intersection point. So in that way, so in that way you can analytically calculate the precise value of this intersection point. And from this mathematical graph, like, you can have a rough or qualitative idea about how the function behaves for smaller values of x, for larger values of x. So what function will change with what rate, and where where they can intersect, and all these things. So is there any question? Okay, so I guess not. So let us proceed. So in the way, from the plot function, you can compare different function and all this. So so let us now take two very popular function, this Gaussian and Lorentzian. So why they are, so they are very much naturally occurring in physics. So why, so when we are dealing with this harmonic oscillator, so this is very well known harmonic oscillator equation. And if we want to plot the harmonic oscillator solution in frequency space, and if the oscillator has some kind of damping, so let us uh, write down the equation. So suppose we are given the equation x double dot plus gamma x dot plus omega square x equal to 0. So this is our harmonic oscillator equation with damping. And so and if we want if we solve this equation in Fourier space, so in what does this Fourier space mean? So we are seeing the response of our x function as a in frequency domain. So in frequency domain, it will have Lorentzian kind of shape. So if we want to see the response with frequency, so this is frequency axis and this is x with respect to omega, then our x will be of this kind. So this x has a Lorentzian kind of shape, and this harmonic oscillator, this is really important in physics. Like it occurs in various topics. So let us learn. Let us get a feel about this, how this Lorentzian function behave and all that. So Lorentzian function is typically represented with this by this. So x square a square by x square plus a square. So this is our function which will which is Lorentzian. So let us plot this function. So and the value of a, so that we want to manipulate. So we have to write the manipulate command. We want to see how the function change for different values of a. So manipulate, and we want to plot uh, a square divided by a square plus x square. So this is our function which we want to plot, and then we have to define the limit. So let us take the value of x to be from -10 to 10, and we want to manipulate the value of a. So we have to specify the value of a. So suppose a is from 1 to 10. So we have to so the full curve is not showing here. So we have to write the command plot range, and so we want to plot the all of this value. So plot range. Okay. So this we have to write inside the plot command. So take my from -1 to 1. So, yeah. So now we are observing the signal from this from the y value from -1 to 1, and we can see that this is the shape of the Lorentzian. So what will happen if we manipulate the our value of a? So if we click on this plus icon, so here here we can see the value of a that is currently taking. So we can change the value of a. So like we can increase. So if we increase the value of a, then we can see that the width of this Lorentzian function, so the full width at half maxima, we can call this at the, so this width is changing. So and if we look carefully, so if we increase the x limit, so we can see that the value of this Lorentzian function, it is asymptotically approaches to this uh, y equal to 0 axis. So the so this function, this for larger values of x, it will reach asymptotically reach the y axis for y equal to 0 axis. That means this x axis, and if we keep increasing our a, then its width will change. So in that way we can get the feel about how the Lorentzian function depend on the value of this a, the parameter a. So let us now take another function, the Gaussian function. So the Gaussian function is typically represented in this way. So this is our Gaussian function. So uh, uh, let us plot this function, and let us check how the function changes with this value of a. So for that we have to again write the command manipulate, and what we want to manipulate the plot. So what do you want to plot? We want to plot e to the power minus x square divided by a square. So where a, the value of a, that we want to manipulate, and we will plot this for in the x limit from -10 to 10, and we have to write down the value of a. So from 1 to 10, and we want to plot the range. So to specify the plot range, and let us take the limit from -1 to 1. So if we execute this, yeah, so this is our Gaussian function. So if we change the value of a, then also you can see that its width is changing. So now we want to compare this Gaussian function and this Lorentzian function, and how we want to plot them on a single graph, and we want to see how they are changing with this value of a. So let us do that. So we have to plot both the functions here. So one is exponential minus x square divided by a square, and so this is our first function, and the second one is our Lorentzian function. So that is a square divided by a square plus x square. So these two are our function, and we have to define the limit of x now. So x is from -10 to 10, and since we are plotting two graphs here, so it is good to insert the legends of this graph. So let us write down that plot legends, and we will insert the uh, or we can write down simply. So if we write down, the first one is our Gaussian, so we will write Gaussian, and the second one is our Lorentzian, so we will write down here Lorentzian, and we want to also specify the plot range. So plot range, and you have to press the arrow, and we have to specify the range. So from -1 to 1, and here we have to write down the parameters which we want to manipulate. So here we are manipulating a, so let us write down a. So this from point, suppose from point 0.5 to 10 we want to manipulate this, uh, and let us see. Yeah, so I think this we can reduce. Yeah, so this is our Gaussian, and this uh, orange one. So this is Lorentzian. So you can see that the Lorentzian has a higher width compared to the Gaussian for the same value of A. So if you want to think of this, so in case of this harmonic oscillator equation, this harmonic oscillator equation in this frequency space, it takes this Lorentzian form because of this damping factor, because of this gamma. It is taking the Lorentzian form, and if there is no damping factor, then it will then its response will be like this delta function, Dirac delta function. So in this, yeah, this is very bad drawing. Yeah. So if we don't have any kind of damping, then our response of this position in frequency domain, so it will have this kind of delta kind of function. And if we have this gamma factor, that means this damping. So for that, the equation take the this kind of Lorentzian shape. So and we can see here that for the same value of A, this Gaussian one, this has lower spread than this Lorentzian one. So in that way, you can compare different kinds of plot on the same graph. So does anyone have any question? Mm, I guess no. So does anyone have any kind of queries from the lecture session that uh, of this week lecture session? Okay. So let us proceed further. So uh, this plot function. So this is for a continuous variable. So suppose you have sine of x, and we want to plot this function with for a range of x. Now, if we have any discrete kind of value. So suppose we have the value of. So suppose we have value of x in discrete, like 0, 1, 2, 3, and this kind of, and we have another value. So for specific values of x, y is taking some specific value. So and if we want to do this kind of plot, then we will have to do this. We will have to write down the least plot function. So suppose let us plot the two functions. So suppose we have a polynomial and a factorial. So polynomial means, so let us write down polynomial. So for that we have to use the common table. So in table we can write down this. So simplicity let us take n only, and we are specifying the limit of n. So n is from suppose 1 to 10. So this function polynomial, it will take this value 1, 2, 3, and all this. So now if we multiply this with 2, then it will take the value. Okay, sorry. Yeah. So then it will take double of this. So any function of n you can write here, and you can specify the value of n in for which values you want to calculate. So if we don't specify anything, so then n will increase in steps of 1. So you can write down here n square. Yeah, and it will take this values. So let us take a simple polynomial, suppose n to the power 4. So this is our polynomial value, and let us take another function. So let us use factorial. So factorial is written in this way, n factorial, and let us specify the limit of n from 1 to 10. So if we So this is the value of this factorial. Now we want to plot both of this function, this polynomial function and factorial function, on the same graph. So for that, what we will do? So here the plot command will not work because these are list of values. So it has some discrete values. So that is why we have to use a list plot. So we are plotting here what? We are plotting. So first, let us only plot this polynomial one. So poly. So in this plot, this x-axis, this is our value of n. So 1, 2, so we have given the value of n from 1 to 10, and this y-axis, it denotes the value of this n to the power 4. So these are scatter points. So if we want to join this point, then we have to write down the command join and this arrow. True. Yeah. So if we write down this command join true, so it will join all the point and so this is our polynomial function. So now let us plot this factorial one. So this is our our the factorial function. So if we want to compare now these both functions, this polynomial function and factorial function, then we have to plot them on the same graph. So for that, let us do this. So factorial, yeah, and now we want to insert the legends. So plot legends, and we have to specify which graph is for which very function. So for the first one we are plotting here is polynomial. So we will simply write down here polynomial, and the second one we are plotting here is factorial. So we will write down factorial. So if we look at this graph, so this is the behavior of this polynomial function and factorial function for with increasing value of n. So as we can clearly see that this factorial one, it is increasing very sharply compared to this polynomial one. So from this list plot, you can compare different functions which have different set of discrete values, and so like this polynomial function and factorial one that we have done here. So does anyone have any question? Shubhankar Datta. So do you have any question? No, Shubhankar Datta is not here. Okay. So if not, let us proceed further. So another important concept is the plotting of this vector field. So this plot function, this is for a one. This is for a function that depends on only one variable, or this is plot for a scalar field. So now suppose we have a vector field. For that, so how we will plot this? So let us take a vector field. So suppose we are given a force equation. So suppose x I cap y j cap plus z k cap, very simple one, and we want to see how this force will look like in the vector plot. So let us plot this function. So for that we have to write this vector plot, and we have to specify the components. Uh, so suppose we are taking here only a two-dimensional function, then we will have two component. One is for x-axis and another one is for for y axis. Then we have to write this as x comma y, and we have to specify the limits of this variables. So suppose x takes value from -10 to 10, and y it takes the value from -10 to 10. So this is how this vector field uh, look like. So if we so you can see here that this function this from this graph, that this x I cap plus y j cap, it has kind of divergence, because if we consider here any element, then we can see that the flux are coming out. So it has divergence. And does this have any curl? So curl basically represents the sense of rotation. So if a given vector field has non-zero curl, that means it has kind of it has a kind of rotation. If we visualize this in vector plot, so here we here you can see we don't have any sense of rotation. So that means the curl of this vector field, that x I cap plus y j cap, so that is 0. So let us plot another field. Yeah. So if we look at, so there is clearly a sense of rotation. So this vector field minus y I cap plus x j cap. So this has a non-zero curl, but there is no but the divergence will be 0, because if we consider any flux where here, so there is no net flux going out. So that is why this vector field, it has non-zero divergence and 0 curl. Now let us plot another vector field. So suppose we are given the force equation x by r cube I cap plus y minus 1 by r cube j cap, where r is this x square plus y square. And we want to visualize this force or this vector field in our plot. So so let us do that. So for that we have to write down the command vector plot. And what is our x component? Our x component is this x by r cube. So let us write x by r cube. We haven't specified yet the value. What does r signify? So we will write down that in a few seconds. And in the y, in the j axis, we have this y minus 1 r cube. So we have to specify the value of r, because the r is not yet specified, and the r is root under, sorry, r is this root under x square plus y square. So we have to replace the value of r. So the replace command in mathematics is written that way. So it will replace the value of r with this. So we have to write square root of x square plus y square. So if we write down the comment, then the r that we have written in here, that will be replaced by the square root of x square plus y square. And now we have to specify the limit of this x and y. So let us specify. So x as from -2 to suppose, and the value y. Let us suppose it has value from -2 to 2, and let us look how this look like. Yeah. So this is the vector plot of this function that we have taken here, and in that way you can plot the field field lines compared to any vector field. Now here this arrows, the length of this arrow, they denotes the strength of the vector field at that point. So if we don't want to denote the strength, we just want to denote the direction of this vector field, then we have to replace the vector plot with the stream plot. So if we write down the same command for stream plot, so let us write down the same for stream plot. So y minus 1 divided by r cube, and we have to replace the value of r. So r we have to replace with square root of this x square plus y square, and we have to specify the limits of this x and y. So -2 to 2, and the limit of y is from okay. So it's just flip. Yeah. So here we can see that the length of the arrow, that is same in all places. So the here the length of the arrow, that does not signify the magnitude of our given function. So this basically represents the direction at that point, the direction of the vector field at that specific point. And now suppose we want to exclude some region from this plot. So suppose then we have to write down the following command. So we have to write down this command, region function. Mm, so you have to write down inside. I think that is region function. And here we have to write in this way: x, y, vx, vy, and n. So here this x, this vx and vy, they represent the component of the x component, y and y component of the vector field, and this n denote the norm of the vector field. So and after that we have to uh, impose the condition that we want to impose. So let us write down this. So let us suppose n should be greater than 0.1. So I think So there is this spelling mistake. Yeah. So if we change the conditions here, so suppose let us put this zero point 0.6 or something. Yeah. So in if we imply different kind of condition, then the plot will be plotted excluding that value. So here what it is happening, so it is happening here that the norm, so this plot, the region that it is plotting, so for that region the norm is less than zero point 0.6, and if the norm is greater than zero point 0.6, that region is not plotted here. So in that way you can with the given condition you can manipulate in which range you want to plot and what are the conditions that you want to imply. So you can imply you can impose more conditions. So you can write down and some vx greater than. Yeah. So in that way, you can imply more conditions or which you want to impose on your plot. So this so this stream plot, they will basically give you the field in which direction the field is going. So and if you want to, so the length of this arrow, they will not represent the strength of the field at that point. So if you want to get the strength of the field, so for that you have to write down stream density plot. Let us remove this condition. Yeah. So here this color will represent and the shading of the color, they will represent the strength of this function. So let us increase the limit, suppose. So in that way you can plot more range if you want. So so does anyone have any kind of question? Okay, no. So we'll take a short 5 minute break and we will continue after 3 minutes. Okay, so let us continue. So another important part of this Mathematica is to solve any given equation. So suppose we have we are given a function. So suppose we have given it this function ax to the power n, bx to the power n minus 1, cx to the power n minus 2, sorry, d0 something. So this suppose we have this polynomial equation and we want to find the roots of this equation. So this equation will have n roots. So from so in Mathematica you can easily find the root of any given equation. So suppose you have been given equation x square minus 2x plus 1. So if we solve this equation, so analytically or this equation is exactly solvable. So if you solve, it will have this x minus 1 squared. So the value of x will be 1 and 1. So now if we want to solve this in Mathematica, so how we will solve this? So we have to write down the command nsolve. So nsolve basically solve this polynomial equations. So and suppose we have this equation x square minus 2x plus 1 equal to 0. So this is our equation which we want to solve. So and we want to solve for which variable? We want to solve for x. We want to find the value of x. So if we write down this, so yeah, so here you can see that it gives our solution of the given polynomial to be 1 and 1. So let us take another polynomial. So let us take of higher order. Suppose x to the power 5 we have. So x to the power 5 minus 3x cube plus 4x square minus 7. So let us take any arbitrary equation and we want to solve this for x. So if we write down this, so you can see that the value, so this is, since this is a fifth order polynomial, so it will have five solutions. They may be or may not be real. So you can see here that the five solutions are this, and here we can see that this it has this solution as three real solution and two complex conjugate imaginary solution. So from complex analysis theory we know that if a given equation has a complex solution, then there must be another solution which and another complex solution which will be complex conjugate of that. So what does that mean? So that means if a given equation has solution of this kind, a plus bi, then this equation must have a solution of this form, a minus bi. So this is well known, and you can see here that this is the case. So this is our this complex solution, and this is the conjugate of the solution. So in that way, you can solve any polynomial of any order, and you can find the value of the solution. So now, suppose you don't want the complex part. You only want the real part of the given equation. So for that, what you will do? You will write down the following command: nsolve. So your equation is this: x to the power 5 minus 3x cube plus 4x squared minus 7 So this is our given equation. Now we want to only know the real part of the solutions. We don't want the complex part. We are only interested in the real values. So what we will do? So we will write down here reals. If we write here, so the it will give all the real solution that the equation has. It will ignore the complex solutions. So these are our the three real solutions that we have given here. So this is solving one equation. So you can solve more than one. So this equation has one variable. You can solve equation with two variables also. So what does this equation look like? So suppose we have two equations. One is ax plus by and another one is cx minus dy. So suppose this is d0 and d1. So suppose we have these two equation and here we have two variables. One is x and another is y. So these are our variables. So this type of equation, they are known as coupled equation. So why coupled? So here the in both the equations we have both the variables. Here we have x and y. Similarly here we have x and y. So that is why they are coupled. So the value of y that will affect x and the value of x will also affect y. So this type of equation are known as coupled equation. So these coupled equations can also be solved from mathematical. So using the same command, so you can solve them in the following way. So let us take two equations. So as we are taking more than one, so this is x square plus suppose y cube equal to 1. So this is our one equation and we have another equation. So let us take that first order. So suppose 3x plus 2y and that is equal to 5. So this is our two given equation and we want to solve. So for that, so in the previous case we are only uh, mentioning x. Now we want to find the value of both x and y that that will satisfy both the equations. So we have to write down here x and y. So and if we calculate this, so basically these are our given a solution. So this is one pair of solution x minus 3 and y minus 2. So in this two equation, if we put down this x equal to 3 and y equal to minus 2, so the both the equations will be it will satisfy both the equations. And similarly this is another pair of solution. So if we put down the value of put plug into value of this x and plug the value of y, then they will satisfy the equation. So and in so these three are basically the pairs of values which will satisfy both the equation. And similarly we can also in the previous manner. So if we write down here reals, so it will basically only give us the real solution that will satisfy both the equation. So in that way you can solve any kind of equation with the help of this command n solve. So is there any question? Okay, so if not then we can proceed. So let us back to the plot function. So so from the plot uh, I was mentioning that we can easily calculate the or we can analytically see how a function behaves, like if it is continuous or if it is differentiable and all these things. So let us plot a simple function. x mod x. So for modulus of x, we have to write down this absolute. So this is our given function, and we want to calculate this in x range of -10 to 10. So you can see that this is our solution, or this is the plot of this function. So you can see that the function is continuous everywhere, and there is no discontinuity, or there is no cusp in the given function. So that means it is also differentiable also. So you can check also the continuity or differentiability of any function by looking at the plot of the function. So let us plot this only mod x. Yeah. So here you can see that around this zero value, so this has a cusp kind of, and if we if we want to calculate the derivative of the function around this point, then we will see that the derivative will not exist, though the function is continuous. But if we want to take the derivative of a function, then at a certain point, then we have to uh, calculate the value of the function from that point to the uh, in infinitesimally positive point, positive side and negative side. And we can see that around this 0 point, uh, uh, if we take a small positive value around this, and if we take to go to the delta in the negative direction, and if we want to calculate the derivative, then you can see that it will diverge. So you can have an idea of any kind of functions from this one. And let us now move to the inverse functions, this trigonometric functions. So let us plot this. Suppose we will plot this tan hyperbolic inverse. So for tan hyperbolic inverse, we have to write down this. Yeah. And we have to specify the limit of x. So let us take from -10 to 10. Yeah. So this is our the tan hyperbolic function. So as you can see that for larger values of x, if we increase the value here, yeah. So it is asymptotically approaching this x equal to around -2 axis, and in the positive side it is as asymptotically approaching this x equal to around this 1 or 2. I mean, in that region it is as asymptotically approaching. So this is the behavior of this tan hyperbolic function. So we can check other hyperbolic functions also. uh, so basically tan inverse this is. So if you want to check this tan hyperbolic, yeah. So this is our tan hyperbolic function. So if we look at this, that then we can see that for larger values of x, so it is asymptotically approaching this y equal to 1, and for negative values of this x, we can see that it is approaching this y equal to -1 axis. So let us plot other functions also. So let us plot this cosine function. So let's reduce the limit. And first insert this plot. So in that graph, this cosine hyperbolic x has very larger value compared to the tan. So if we want to see both of them in the same graph, then one thing we can do, so we can introduce the log function. So what is the, so how will it resolve? So basically, if we have any kind of so suppose we have two polynomial x to the power n and suppose x to the power m, and suppose n has value of 5 and m has value of 500. So if we plot both the graph on the same if we plot both the function on the same graph, then we will barely see the effect of this because this will have very large value compared to this. Now if we want to see the how both the function, how the function behave, or both the function at the same time on the same graph, then we can introduce the logarithmic function. So what is the advantage of this? So if we calculate the logarithm, then it will be n log x and it will be m log x. So the power in the function that comes in the outside, and that is now behaving as a multiplying factor. So this is just 5 log x and this is 500 log x. So now the increase will be much lower and you can see the effect of both the function. So if we do in the same way, so let us plot, write down log here and log also. Yeah, so here you can see how both this logarithmic of tan hyperbolic and logarithmic of this cos hyperbolic behave, and we can see effect of both this in the both of them in the same graph. And we can also specify the plot range, or if we want to specify some certain range, then you can write down here. Suppose you want from -5 to 5. Yeah, so in that way you can manipulate or uh, so does anyone have any kind of question? Okay, so if not, then we can proceed. So we can also multiply these functions with a certain value, and by manipulating the b- value of that parameter, we can see how this changes. And so now let us again compare different function and see how they behave. So let us take two functions. So let the first function is x to the power half log x, and the second function is e to the power minus x into x to the power one third. So let us check how the function look like, and what are their properties, how they behave in the for the large values of x and for smaller values of x. And so this is one thing we will do. And the second one, so we will take root under x to the power one third x square and all these functions, and we will check how they behave in the large x in the large x limit and small x limit. So let us proceed. So let us do the first one. So this is our one function, and the second function is e to the power x to the power one third. So this to our function, and we have to specify the limit of x. So let us take x from minus 10 to 10 and insert the legends here. So this blue one, this is for x to the root under x log x, and this orange one, this is for e to the power minus x and x to the power one third. So let us zoom in the region from 0 to 1. So the limit of x, let us specify this from 0 to 1. Yeah. So if we look here, uh, so the function root under x log x, so it basically it kind of has a minima around this point, and after that it is increasing. And if we look at this function e to the power minus x x to the power one third, so it has a hump. So it is first increasing, and it attains a maximum value, and after that its value is decreasing. So if we increase the limit, so then we can see it is asymptotically converging to this y equal to 0 axis. And so basically this function, it has a it has a maxima. This yellow this orange one, exponential function, it has a maxima, and after that its value is decreasing. And this blue curve, that means root under x log x, this function, it has it has a minima first, and after that it is uh, increasing, and they are intersecting at one point around this 1.5 or something value. So we can analytically calculate the minima position or the maxima position. So let us calculate the minima position of this x to the power half log x. So for that we have to calculate the first order derivative and second order derivative. So our function is x to the power half log x, and we want to find the minima of this function. So for minima, the condition is that del f del x, it should be 0, and del 2f del x square, it should be greater than 0. So this is the condition for minima. So let us check. So let us do the derivative. So it will be x to the power half into 1 by x plus half into x to the power minus half log x. So this has to be 0. So if we evaluate this, this will be x to the power minus half and this will be half into x to the power minus half log x. So it will basically have the value 2 plus log x equal to 0. So log x equal to minus 2 x equal to e to the power minus 2. So basically this is our extrema point. So it can be minimum or it can be maximum. So for that we have to check the second derivative. So our first derivative is this, and we have to again take derivative of this function. So let us do that. So the first derivative we have is, so let us denote this by g. So g is x to the power minus half plus half x to the power minus half log x. So now we want to take derivative of this function again. So if we take derivative, it will be minus half x to the power minus 3 by 2 plus half x to the power minus half, and it will be 1 by x, and we will have, so these two, this one and the first one and second one, it will cancel out, and we will left with this 1 4 x to the power minus 3 by 2 into log x. And we, for minimum, for this extrema point, the value of log x is minus 2. So if we plug in the value here, so it will be minus 1 by 4, and we have x value to be to the power minus 2 minus 3 by 2, and log x is minus 2. So this is positive. So that means around this point e to the power minus 2, it this function, this x to the power half x to the power half log x, it has a minimum. And we can also see this from this graph. So if we lower this limit, so 1.5, so you can see that around this point 15 or something, this function has a minimum value. So you can analytically check what the minima or maxima is, and you can plot the function at the same time. So does anybody have any question? If no, then we can proceed. So we will again back to our this solving of this polynomial equation. That means this n solve. So what we will do now? So we will take, so in the previous time, what you have solved? We have solved a equation for a given coefficient. So like x square minus 3x plus 2 or something. So for these coefficients which are given, now we want to solve this for a variable coefficient. So suppose we have equation of this x square plus ax plus 1, and we want to we want to see how the solution of this equation, it changes with the value of a. So it may happen that for a certain value of a, our the solution of this equation, it may have a transition from real value to imaginary value. So we want to study these things, how our given equation, it changes for a value of a. So you can or you can similarly also study this x square plus x plus b, and also see how, so we can basically manipulate any of the coefficients, and we can see the effect of the coefficient on the given equation. So let us do that. So we will solve this equation. Suppose x is square minus 3x plus 1 for x, and we will get this value. Now suppose in place of 3, now we put here a, and we want to manipulate the value of a. So for that we have to write down the manipulate command. So this is our given equation, and we want to manipulate the value of a. So for that we have to specify the limit of a. A can be from 1 to 5, and we want to start the value of a. Suppose we want to start from a specific value, so suppose 2. Yeah, so here if we change the value of a, we can see the how the solutions are changing. So you can see that for this value 1.21, our solution is imaginary, and if we keep on increasing, then we can see that at this point from 1.61 to 2.01, our solution is make a transition from the real value, from imaginary value to the real value. So in that way you can so specify here 2, and you can take a here, and now you want to see how the solution changes with the uh, x to the power 0 coefficient. So you can see that so you can similarly check how the effect of a on the function, on the given equation, how this is changing. Yeah, for a greater than 1, so this equation have imaginary solutions. Now let us do this for another, we can do this for coupled equation also. So let us do this for coupled equation. So for coupled equation we have to specify here two equations. So suppose one is x square plus a y cube, this is 2, and we have another equation, suppose ax plus 6y equal to 1. So this is our two equations, and we want to solve this for value of x and y. And what we will manipulate? We will manipulate the value of a. So you have to write down the limit of a, in which limit we want to manipulate. So let we write down this, and we do this. So here you can see, so this gives the solution of our equation. So if from this slider we can change the value of a, so you can see how the solutions, how the pair of solution changing with the given value of a. So with the, so this manipulate command, so that is very useful and mathematical. So basically with the help of this manipulate command, you can you can see how a given function is changing for a certain parameter. You can see the dependency of the function on a parameter. So suppose in case of this Gaussian function, if we or Lorentzian function, if we keep on increasing it, our this width of this function that increases. And here also you can see that if we so change our value of a, our solution has like goes from this real to imaginary, all this. So for that, this manipulate command, it is very useful in visualizing these things. So does anybody have any question?
Sir, can we only solve algebraic equation using nsolve command?
uh, so another kind of algebraic equation, so basically you can also solve trigonometry kind of equation. And you are asking about that.
Yes, sir. I mean, can we solve transcendental equation using this?
Okay, so let us try trigonometric equation first. Let us check how it is. So let us check that. So suppose we have a given equation of like sine x. Let us take a simple equation. Sine x equal to x by minus x equal to 0. So this is our given equation, and we have to solve this for value of x. Okay, so I think this n solve, we cannot solve this sine or trigonometry kind of function. So it basically only can solve this algebraic kind of equations. So, so uh, I will get back to you the next day, like with which command we can solve this trigonometry kind of function. So what does this solve only do? This also not do. So hello, Tanvir.
Yes, sir.
So I will get back to you the next day, like with which command we can solve this
Sh-
trigonometric or any other kind of functions. So
sure,
it
sure.
seems that for this n solve, we can solve only this algebraic kind of equation, this polynomial and all of this. Okay, so I think this is like for introductory level, I think this is enough. So you all can play with this functions, this plot function and manipulate and all this, and you can see how a function behaves for larger value, for smaller value, and intermediate region and all this. Okay, so yeah, another thing I forgot. So this I want to discuss. So how this functions changes with this value of x. So let us plot all this together. So suppose we have x to the power 1/4, x to the power 1/3, x to the power 1/2. That means square root. And we have x square, and x cube. And we want to see how these functions behave for different regions of x. So let us first check for larger value of x, for how it will behave. So let us take the limit of x from suppose minus 10 to 10. Okay, so we have to insert obviously legend here. So to function, so let us lower the limit. Yeah. So you can see that around this region from 0 to 1, how the functions behave differently from the region above x equal to 1. So we can divide our uh, the range in two range. So let us first look closely. Let us first look from x 0 to 1 and how they are changing. So 0 to 1. Let us increase a little bit. Yeah. So we can clearly see that this brown one, this corresponds to this x cube, like the higher value of the polynomial. So for higher value, for if we have the higher power, for x equal for x value of less than 1, we can see that their increase is not that much prominent. So in that region from 0 to 1, we can see that x to the power 1 fourth, that has the largest value, and this x cube, it has very smaller value. But if we but as soon as it crosses 1, so let us plot from 0.8 to 1.8. Yeah, so then we can see that uh, for greater than one value, this the higher the order of higher the power of the x, the larger the value of the function. So you can see that the x cube has very larger value, and this x to the power 1 by 4, this is very lower value. So we can specify here the plot range. Yeah, so you can see that its value is increasing. So if we increase our limit, yeah, so it is almost disappearing. This values, it has around, this x cube has value around 1000, and this functions of value around this 100 or 60, 70, this kind. So this function, they behave differently in the very smaller x limit and larger x limit. So you can have a feel how a function behave for different range of these values. So uh, you first of all, you have to be comfortable with this notation and all this. So this syntax of this mathematica, because every programming language has different kind of syntax. So if you like work with MATLAB or Python, then the syntax we will use, that will be different from the mathematica. So first of all, you have to get acquainted with how this plot, how to write down this command, how this how we are inserting this legend, and how we are dealing with this plot range and all this. So you have to practice a few days to get acquainted with this syntax, and once you are comfortable, then you can easily see, you can do this kind of things. So does anyone have any question? Okay, so if not, then I think this is fine for the uh, first week. And regarding the assignment problem, so if you have any question regarding the assignment, so you can ask me about the first assignment question in the next week. So what is your deadline for the first assignment? Hello, is it
Sir, I think that deadline has already passed.
okay? So if the deadline is passed, then you can ask any specific query regarding the assignment, or how uh, like if you want to have, if you want to know the solution of any specific question, then you can ask. Okay, so this is it for the first week. So we will meet on the next Saturday at 6 p.m. Okay, so bye.
Thank you, sir.